In the previous few lectures we were discussing about the weighted residual method and several forms of that, including its discretized form in terms of the finite elements method. We will proceed further with that one, but before that let me give you some homework exercises which you can solve by considering the discussions that we had in our previous couple of lectures. So, the first problem, consider the differential equation with the boundary conditions solve the above equation using say least square point collocation Galerkin and Rayleigh-Reed's method. For the methods where you require to choose a trial function, you can choose a trial function u equal to a sin pi x, where a is the undetermined parameter. So, we have worked out similar examples in the class, so you can use that concept to solve this problem. Second problem, consider a heat conduction problem with the following governing differential equation: d dx of a k dt dx plus q equal to 0, where a is equal to 10 meter square, k is equal to 5 joule per Kelvin meter second, q equal to 100 joule per second meter. This problem is valid within the domain x lies between 2 centimeter to 8 centimeter. The boundary conditions are T at x equal to 2 equal to 0 degree centigrade and the heat flux at x equal to 8, both are centimeter, 2 centimeter and 8 centimeter, is equal to 15 joule per meter squared second. Obtain temperature distribution in the domain using finite element method with 3 linear elements and compare with the analytical solution. Okay. So, these are the two problems that you can try. The second problem you can try by hand because there are 3 linear elements, but I would prefer that you first get familiar with it by trying it by hand and then write a computer program to regenerate the same solution and check whether your program is working fine. Okay. Now, we will move on to our subsequent discussions, and when we say subsequent discussions we have to keep in mind that our agenda, broad agenda for all these discussions was to introduce the fundamental concepts of discretization. We have introduced one concept of discretization by going through the roots of variational formulation, but that is not all. That is not all, because variational formulation is one way of arriving at the discretized equations, but one could have other possibilities, because one has the differential equation in its D form, variational form is a variant of that, and one could have M form from that one. So, we have till now focused our attention on V form, and similar concepts could also be valid for M form, because like we have seen that under certain special circumstances these forms are interchangeable. So, you could derive, for example, finite element equation starting from the M form, provided the M form exists, and it is physically a very meaningful way of deriving some of the finite elements equations, because M form sometimes has a very important physical meaning. Like if you are solving a structural mechanics problem, then M form essentially is the statement of minimization of potential energy of a system, which governs the stability of a system in equilibrium. So, if you minimize the potential energy of the system, then that will give you the equilibrium configuration. So, the numerical method turns out to be consistent with the physical requirements as well. So, M form also happens to be physically appealing, but it is possible to derive discretized equations without going through these routes, but directly through the D form, and one such method which does that is known as the finite difference method. So, what is the basic philosophy of the finite difference method? What we do is, in the governing differential equation we manipulate with the governing differential equation directly rather than through its V form or M form. So, we use the D form. In the D form there are expressions for derivatives, and we express the derivatives in terms of suitable algebraic differences by using the Taylor series expansion. That is what is the basic philosophy of the finite difference method. So, express derivatives in terms of suitable algebraic differences by using Taylor series expansion. Let us see a simple illustration of how we do it. If you have a domain like this, say a one dimensional domain, we divide the domain into, or we identify a few numbers of grid points. So, we actually do not divide the domain into a number of subdomains in the meaning of an element, what we do for finite elements, but what we do is essentially we do a very similar thing, because essentially we represent the domain by a collection of discrete grid points. So, these grid points are similar to the nodes of a finite element method, but there are conceptual differences, because you here you do not have logical elements which are connected by the nodes. Here you have just discrete grid points. Now how they are logically connected or how they are laid out is a matter of choice of the geometry rather than, or it is a matter of choice of the coordinate system, so to say, rather than having some particular shapes corresponding to each element. So there is no concept of element as such, but you have just discrete grid points. So let us say that you have some grid points, say I, you could have I plus 1, I minus 1. In a 2-dimensional framework you could have the other direction. So here then you would have got I comma j, I plus 1 comma j, like that and so on. Now we are just considering a 1-dimensional example to begin with. Of course we will go into more details in our subsequent lectures, but the objective of this part of the lecture is to introduce the method rather than going into more details of the method. So what we will do, we will try to write a function. Let us say I represents the point x and this distance is h and this distance is h. So we are interested in expressing f x plus h, where f is any function, let us say temperature for a heat transfer problem, in terms of f at x. That is, we are interested to express the value of the variable at I plus 1 grid point in terms of the variable at I grid point. So f x plus h is equal to f x plus h f dash x plus h square by factorial 2 f double dash x, so on. This is the Taylor series expansion. So let us say this is equation number 1. Similarly, you could also write f x minus h is equal to f x, replace h with minus h. So this is by keeping the point I minus 1 in mind. Now let us say that we are interested about an algebraic expression for f dash x. So there could be different ways in which you could derive that. For example, you could write f dash x from equation 1 as f x plus h minus f x divided by h minus h by 2 f double dash x and so on and so forth. So if you truncate the Taylor series up to this and try to use this as a formula, so you can see that you are replacing the continuous derivative as a discrete difference quantity, and since it is not exactly the same, it is inaccurate, and the inaccuracy is attributed to several things. Later on we will study that what are the sources of errors in these discretization methods, but at least we can intuitively guess one particular type of error, that is we have truncated the Taylor series up to a finite number of terms, and that is the one of the sources of the error. So that is called as a truncation error, and the truncation error is here of the order of h, because this is the leading order term. So we expect that h is small for this implementation to be accurate, and if h is small, the subsequent terms like h square, h cube, they are expected to be smaller than h, and hence the truncation error is dictated by the leading order term, that is of the order of h. Similarly, from equation 2 you could write f dash x is equal to f x minus f x minus h divided by h plus h by 2 f double dash x. The terms which are remaining and which are not considered, whether it is plus or minus is not important, only the order is important, because anyway we are interested about the truncation error. So, if we truncate this expression up to this, then the truncation error is of the order of h. We can also find out f dash x by subtracting 2 from 1. So, that will give you f dash x is equal to f x plus h minus f x minus h by 2 h. Then, so when you subtract h square by factorial 2 term gets cancelled out. So, h cube by factorial 3 into f triple prime x that remains. So, that into 2. So, h cube by 3. So, h cube by 3 f triple dash x by, so it is h square by so it was 3 factorial and that multiplied by 2, so that it becomes 3 and divided by 2, yes. Now, so whether it is plus or minus sign, let us just check. So, it will be f dash x, if you keep on one side then it will be minus, right, but at the end it is not important again whether it is plus or minus, only the order is important. So, the truncation error is of the order of h square. So, these are known as different ordered difference formulas. So, this is forward difference, this is backward difference, and the third one is central difference. Corresponding to the first order derivative. So, these names are quite clear, I mean why such names do appear, because forward difference as if you are going forward from x to x plus h, backward as if you are going backward from x to x minus h, and central means x is central to x plus h and x minus h, it is the midway. So, the names are quite matching with the corresponding implications. Now, this is about the first order derivative. You can do similar things with the second order derivative. So, let us try to do that. Let us say we are interested about f double dash x. So, to get f double dash x, what we can do, we can add 1 and 2. So, if you add 1 and 2, you get f x plus h plus f x minus h is equal to 2 f x plus h square f double dash x, then h cube by factorial 3 term gets cancelled out. So, you have h 4 by factorial 4, into 2, that means H4 by 12. So, from here you can write f dash x is equal to f x plus h plus f x minus h minus 2 f x divided by h square minus h square by 12. So, this formula where you can truncate it up to this term, this is known as central difference for the second order derivative. And truncation error of the order of h square. You can also express the second order derivative in terms of differences in the first order derivative. For example, you can write f double dash x as f dash x plus h minus f dash x divided by h. What formula is this one? Which difference? Forward difference, backward difference or central difference? This is forward difference, right? Now you can write individual f dash terms in terms of f by considering the first order difference formula. So you can write this as f x plus h minus f x divided by h for f dash x plus h. So which formula is this one? Backward difference. Similarly, for f dash x, f x minus f x minus h divided by h, the whole thing divided by h. So f x plus h plus f x minus h minus 2 f x by h square. So the central difference formula may be perceived as two successive steps of one forward difference and another backward difference formula for first order derivatives. It is the manner in which you perceive it is the ultimate interpretation, but eventually whatever may be the formula, it may be generated by the Taylor series expansion. That is the simple way of looking into it. Next is, how do we make use of this formula? To understand that, let us consider an example. Let us take the same one dimensional steady state heat conduction problem. This is the example. So we take the same problem which we considered for illustrating the finite elements method, that is d dx of k dt dx plus s equal to 0, and we considered k to be constant for the particular example that we chose. The boundary conditions, so we considered a rod from x equal to 0 to x equal to L. At x equal to 0 it is insulated, and at x equal to L it is given temperature. So now let us write the corresponding derivative in terms of a difference quantity and see that how the corresponding finite difference looks like. So, if you express it in terms of a difference quantity, you of course are free to choose forward difference, backward difference, central difference, whatever formula that you are interested in. The central difference is a good one because its error is of the order of h square. Now, if you use the central difference formula, our assumption is k and s both are constants. So, you have f x plus h, that is T I plus 1 plus f x minus h plus T I minus 1 minus 2 f x minus 2 T I divided by h square. What is h? H is the distance between the grid points. Now, if it is a non-uniform distance between the grid points, then obviously h for one particular term and h for another term, they will be different. So, when you are writing f x plus h in terms of f x, then there is one h. When you are writing f x minus h, that h may be h 1, another different h. So, this h may be h 1 and accordingly the algebra will change, but basic philosophy will remain the same. For illustration we consider the same h, although it is not necessary that one has to use same h. Why is it not necessary that we have to use the same h? What will dictate that whether we should use a large h or a small h? In a domain there may be locations where the temperature gradient is very large. To capture that you require grid points which are spaced in a very fine manner. So, they are very closely spaced or densely spaced. On the other hand, there may be parts of the domain where the temperature gradient is not that steep. So, you can use a coarser grid at those locations. So, obviously depending on the physics of the problem you can economize it by choosing finer grids and coarser grids. It is not necessary that everywhere you use fine grids, that will unnecessarily increase the computational cost. So, wherever there is a less steep gradient you use coarser grids. So, it is possible and it is very much practical that in a particular problem you have non-uniform grids. So, this example is an illustration with uniform grids, but similar algebra can be arrived at with non-uniform grids, the expression will be different. Then plus s equal to 0. So, what we have basically done is, since k is a constant, we have taken it out of the derivative. So, k d square t dx square, in place of d square t dx square we have written the difference expression. So, from here you can write T I or T I plus 1 plus T I minus 1 minus 2 T I plus S h square by k is equal to 0. So, you have an algebraic equation involving T I plus 1 and T I minus 1. So, if you have, let us consider 3 elements and see that how we can assemble it. Again, when we say 3 elements in finite difference, there is nothing called an element, so it is just for our own perception. So, we consider basically that there are 4 grid points, but that does not mean that it has 3 elements, because concept of element is not there. So, it is just some isolated points 1, 2, 3, 4. So, the domain is now just a collection of 1, 2, 3, 4 points, disregarding how they are connected and all that is that information is not a part of the finite difference method. So, you can write this, remember that these equations are valid, this equation is valid for the internal grid points, not the boundary, because when you consider the boundary say 1, you require basically 3 grid points at a time, one to the right, another to the left, there is nothing at the left of the boundary. So, it is not valid at the boundary, it is valid only at points 2 and 3. So, for point 2 you have T3 plus T1 minus 2 T2 plus SH square by K equal to 0. This is for the grid point 2. For the grid point 3, you have T4 plus T2 minus 2 T3 plus SH square by K equal to 0. Then you have the boundary condition, say T4 is equal to TL, that is given. So, that is given, but still you have T1, T2, T3 as 3 unknowns. So, you require another equation. Obviously, grid point 1 will give you another equation. So, for grid point 1, what is your corresponding governing equation? That you have to derive from the boundary condition. So, this was grid point 4. For grid point 1, boundary condition is the heat flux is 0, that means K dt dx at 1 is equal to 0. So, you can write it in terms of a difference formula T2 minus T1 by H equal to 0 as a forward difference formula, where H is the distance between each of the grid points. So, which implies T2 or rather T1 is equal to T2. Remember, when you write a computer program, there is a difference in the statement T1 equal to T2 and T2 equal to T1. Always when you are writing a statement for a boundary, that means you are writing the expression for the boundary condition. So, express the boundary as a function of the interior, that means there is some value T2 which is assigned to T1, which is the value at the boundary. So, it is not T2 equal to T1. Of course, when you do it by hand it does not matter, but when you do it through computer programming, it is the boundary assigned in terms of interior ones. That is how you have to organize the boundary conditions. We will come to the more details on the boundary conditions subsequently, but here the objective is to illustrate that at the end what you have achieved. At the end you have these 3 equations, 3 linear algebraic equations with 3 unknowns. So, you can solve for T1, T2, T3. So, and in between how it varies, it depends on your interpolation, but it has no sense of an element. So, it does not care how you interpolate it, it is up to you, and then so it will give you just the values of temperature at discrete points, and then you can maybe you can smoothly join them or join them by piecewise straight lines, it is up to you. So, this is the basic implementation philosophy of a finite difference method. Of course, we have to remember that is it sufficient to know this implementation strategy? It is not, because many times we may use the same implementation strategy, but the method may fail, the method may become so called unstable, the method may become inconsistent. So, these are certain important terms, and we will see that eventually if these are the cases, then there is a high chance that the method does not converge to the exact solution or even an approximate form of the exact solution that you are looking for. So, mere implementation of the Taylor series expansion is not all, we have to see that at the end whether it satisfies certain requirements which are called as consistency and stability requirements. So, later on when we will be considering error analysis, we will revisit the finite difference method and see that for steady as well as unsteady problems whether any type of discretization will work or not. But again as I am repeating that the objective of this part of the discussion is not to go into the details of the method, but to introduce the method, and that is why we are just restricted to such a simple example. We will take up more involved examples on finite difference method in subsequent part of our course. Thank you.